Yes, class. So yesterday, most of the topics we had completed, but the last portion of your magnetics is left to be discussed. Now see, magnetic dipole, current carrying coil is here. So how to find out the direction of magnetic moment? See, under magnetic moment, you have to find out south polarity and north polarity. So how can you find it? Just see, if you have, let's say, south polarity, north polarity, so the best method is just drop up south polarity, that is S, and wherever the edges are going, wherever the edges are being marked, that will tell you the direction. For example, see, that will give you the direction of current. For example, see, if I drop an S in this circular coil, so and I mark the edges as this. So what will happen when I am marking the edges as this? Current direction is coming as clockwise, right? So that gives me the polarity. Or if the clockwise direction is coming, you can relate it with south polarity. So just remember, anti-clockwise north polarity, clockwise south polarity. This is how you have to find out the polarities if circular loops are provided to you. Now, formula for magnetic dipole moment. Magnetic dipole moment, this is simply area of the coil multiplied by the current. Now, area can be anything. It can be a circular coil as well. It can be a rectangular coil. It can be a square. So whatever is the area for the coil, calculate the area respectively and multiply it with the current. Now, this is valid for a single turn. If you have one turn of coil, one single turn, so you will use A into I. Suppose if I say two coils are present, then what will you do? So for two coils, you will double it. For three coils, you will triple it. So whatever is the number of coils given to you, just keep on multiplying it with it. Fine, NAI. So final formula for magnetic moment becomes NAI. Now direction. Direction is again, wherever the current is moving, you have to curl your fingers, thumb gives you direction. This is the exact direction which we have seen for the magnetic field for a circular coil. This was what we had seen. No, suppose if I give you this figure, first figure. So see, I'll move my right hand along the sense of current. So where is the current moving? Current is going clockwise. So I'll also curl my fingers clockwise. Do you see this? I'll also curl my fingers clockwise. So this is how clockwise the fingers are moving. So where is the thumb pointing? Thumb is pointing inwards. That gives the direction of magnetic moment also. That was the direction of magnetic field. This is the direction of magnetic dipole. For the second figure, quickly tell me in the chat column what should be the direction of magnetic dipole moment. Anti-clockwise, this is given to you, Samaira. Anti-clockwise is the direction of current. I am asking you direction of magnetic moment. Just now I have told you. So yes, Anna is right. Others also? Yes, Samaira, right? Only Samaira and Anna. Abhinav. Sania. Heather. See, for the first figure, I'm again repeating. Wherever is the, whatever is the direction of current, just curl your fingers along the sense of current. For example, in the first figure, and you use your right hand. So suppose in this first figure, the current was moving clockwise. So I also curled my fingers clockwise, right? When I curled my fingers clockwise, thumb pointed inwards. So I could conclude the fact that magnetic field is inwards, and hence whatever is the direction of magnetic field is the direction of magnetic moment. What about the second figure? This is what I'm asking you. If this is this rectangle square, this square is given to you, what will be it? just curl your fingers wherever the current is moving. Clockwise, so clockwise, anti-clockwise, so anti-clockwise. Just check where the thumb is pointing. Is it pointing towards you, that is outwards, or is it pointing towards the page, screen? Yes, outwards. See, if the current is moving anti-clockwise, it means I have to curl the fingers anti-clockwise. This is how anti-clockwise will appear. Where is the thumb pointing? Thumb is pointing outwards. Thumb is pointing towards. No, 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 not inwards. See, no, not inwards. Inwards was for the, okay, you're answering for the first part, right? For the first part, this is inwards. For the second part, this will be outwards. See why? Because when you are curling the fingers, thumb is pointing outwards. This is how you just see the direction, and formula is very simple. If I have this square, I'll just multiply 2 into 2. That gives me the area. I have a circle with a radius 1 meter. I'll take out pi r square and I'll get the area. Just multiply area with the current, and if number of turns are given, multiply it with number of turns. That's it. All right, so just make the heading magnetic dipole moment and write down this S, N, this part, and direction quickly. Fine, I hope you must have written till here. Okay, torque's formula, you should remember the derivation is not a part of You shouldn't do derivation right now. That is of no use to you. See, just remember the formula is magnetic moment, which you have studied right now, multiplied by the magnetic field. Just multiply magnetic moment with magnetic field. That gives you torque. Now, net force will be 0 because all the forces on the loop will be cancelling each other. For example, if this is a rectangular loop, so force upward will be acting upwards. This direction we have seen yesterday. Remember, keep your hand towards the direction of velocity, curl your fingers towards magnetic field, thumbs give you directions of force. Exactly that what we are repeating. So forces above, below, they cancel each other. Forces towards the right and left, they cancel each other. So net force is not there, but torque exists in your system. Net torque does exist in your system. So formula for this torque is magnetic moment, which we have just seen, IA, NAI, and multiplied with the magnetic field. Whatever is the area, calculate the area accordingly. So M cross B, MB sine theta, or you can, if magnetic moment is not given to you, then you can properly use NAI. All right. So net force on current carrying coil is 0 in uniform magnetic field, and this is independent of shape and size. That means whether it's a circle, whether it's a coil, circular coil, or a rectangular coil, the force is not depending on it. It is completely 0. That's why whatever coil you choose, whichever shape is there, this is not depending. All right. So just to write torque, write the formula for torque. Do one thing, class. First write this one, NAIB sine theta, then write this one, and then these 2 points. That's it. Just make torque on current carrying coil as the heading and fine, class. Last topic, that is conversion of galvanometer into ammeter and voltmeter. So first you have to understand what is this device moving coil galvanometer. So just understand galvanometer is there. So basically galvanometer is working on the principle of torque only, which you have studied right now. Torque we have studied. So that same torque will be used, and the principle of galvanometer will be also involving this torque only to rotate the dipole and produce angular deflection. Now see, moving coil galvanometer. Galvanometer is basically a device. That is used to detect the current. If current is present in your circuit with whatever intensity it is present, galvanometer will be showing certain deflection, right? Now, if in your circuit galvanometer is connected and this is not showing any kind of deflection, so if no deflection is there, this means directly that no current is flowing in the circuit. Even if slightest amount of current will flow, slightest amount of deflection will be there, that is for sure. But how much amount of current is flowing, what is the intensity of current flow, that is totally calculated using your ammeter. Fine. Ammeter will give you the exact value for it. Voltmeter will also give you the value for voltage. That is not the work of galvanometer. Galvanometer's work is just to detect the current that is present. Now see, principle of moving coil galvanometer is that whenever this current carrying coil, this is placed in magnetic field. So torque occurs and that torque rotates basically the dipole, rotates it, and what happens? Angular deflection is produced. See, for that you just have to understand the very basic construction of it. Just look at this, how it is constructed. So two magnets are there and one of the sides or the edges of magnets are carved in the form of concavities. Fine. So both the magnets, so that radial magnetic field could be developed. That's why they are carved like this. And in between, soft iron core is present with a pointer. So pointer is held with the help of string and the wire wrappings of aluminium or copper are done like this. Now, what we see, we just see this type device, right? We just see this kind of device where what happens? If current is, this is the sort of galvanometer which you see. If current is there, it will deflect on either sides. This is what we see, but inside it, this is the scale that is just visible to us. Apart from that, there's a whole construction. Permanent magnets are there, pointer is there. Now see, when the magnetic fields come because of the permanent magnet, since we have carved it in the form of concavities, what happens? The magnetic field becomes radial. So radial magnetic field is present. Uniform radial magnetic field is the characteristic of moving coil galvanometer. Uniform radial magnetic. Fine. Now restoring torque acts. It does what? It rotates the spring. Whatever is your waves and SHM and everything that you have studied already. Fine. Now, when the spring rotates, the pointer moves and gives deflection if current is present. Because if current is present, then only we are having magnetic field. And the magnetic field and the torque associated with it, tau is equal to NAIV. That's what we had studied. So torque will come, it will deflect it. This is how the galvanometer works. So under moving coil galvanometer, you just have to know the basic theory points of it. How does it work? Construction you don't need to do. Construction won't come in your exam. Principle you should know. And what is the work of it? That is enough. Now, if you just have a galvanometer, and in a whole circuit, you just have a galvanometer. You do not have any ammeter or you do not have voltmeter. Then how will you find out the magnitude of current or how will you use it? So there's a method. If you have resistors with you, you can just arrange the galvanometer and the resistors in such a manner that it will give you and provide you the function of ammeter. As well as the same thing goes for voltmeter. So how that conversion occurs, that series and parallel connection of resistors occur, and we already know how to calculate the series and parallel combination of resistances, so we are going to use that. So under moving coil galvanometer, you should just know this part. Before moving to sensitivity, just remember there's a deflecting torque, there's a restoring torque. Deflecting torque is the torque that is because of magnetic moment, right? Because of current, magnetic field. So torque is allowing the spring to move. But what is happening whenever there's a system is in SHM, or even if it is not in SHM, we have studied one thing, that the torque, restoring torque tends to bring the object back to its mean position. So deflecting torque will be balancing the restoring torque. Now deflecting torque is NAIB and restoring torque is K theta. This is the condition of SHM also. You must have heard. For linear SHM, we write minus F is equal to minus KX. For angular force, that is torque, we write it as minus K theta. So this is our restoring force, that is the restoring torque that is needed. Now when you equate NAIB with K theta, you get the value of the deflection, that is theta, which is NAIB divided by K. N is the number of turns, A is the area of coil, B is the magnetic field, I is current, and K is the constant, torsion constant. So torsion constant will be given to you, all these values will be given to you. You will be just needing to calculate deflection. Now, depending upon deflection, you have a concept of sensitivity. So sensitivity means what? That in general also we say sensitive when even for humans we also say a person is sensitive. So what is meant by the term sensitive? When for a small stimulus a large reaction is obtained, right? That is what is meant by sensitive. So similarly in the circuits also, if for a very small current, a very small amount of current, the circuit, the galvanometer is showing a huge amount of deflection, then we'll say the galvanometer is sensitive. So in this case also, galvanometer sensitivity is measured by either as current sensitivity or as voltage sensitivity. So this is just what is the physical meaning of it. But mathematically, when you want to show it, what is current sensitivity, what is voltage sensitivity, just take deflection. Deflection just now I have made you see, NAIB divided by K. That formula will give you deflection. Take deflection divided by the current. Just take the deflection divided by the current. All right. And then for voltage also, take deflection divided by the voltage. That's it. So NAIB by K was theta, divided by I gives you NAB by K. And similarly for voltage sensitivity, NAB by K divided by voltage, that is I into R. Here you are going to use Ohm's law. See, theta by V was already there. V is IR. Using your Ohm's law, this is V is equal to IR from your Ohm's law. This is your Ohm's law. So now when you put it, formula for voltage sensitivity is NAB by KR. And even if the definition comes, deflection per unit current, deflection per unit voltage. And this part at least you can do if you remember the formula for theta. So just write down the principle of moving coil galvanometer. All right. After that, write down the formula for deflection and write down the whole table for sensitivity. That's needed. Do not draw the construction part for moving coil galvanometer. Just the principle for it, because these questions are there in the form of statements in your previous year questions. Now, see the conversion of galvanometer into ammeter. So, a very low resistance will connect in parallel with the galvanometer. We call this as resistor as shunt, SHUNT, shunt. So resistance is low and we connect it parallel. Now you just have to remember the basic formula, or even if you do not remember the formula, just remember this one thing. Current will be going across galvanometer. One current will be going across the shunt, right? So voltage across both of them will be same because they are connected in parallel. If they are connected in parallel, voltage across both of them will be same. So current across the shunt, let's say I minus Ig, if I is the total current, and is equal to current through the galvanometer multiplied by the resistance of galvanometer. So on solving this, you get the formula IgG minus I by Ig. Or you can directly write potential difference across shunt is equal to potential difference across galvanometer. So shunt is what? Low resistor device that is connected in parallel. Now, if you just do the opposite, if you take the high resistance and in series, now your voltmeter will be constructed. Fine. If you take the galvanometer, current is flowing through the galvanometer, resistor is there, high series resistor. So galvanometer and resistor, they are connected to each other, right? They are in series connected. So if they are connected in series, you can straight away apply your Ohm's law. So Ohm's law is valid till here. R equivalent is R plus G, current is Ig. So V is equal to Ig multiplied by G plus R. Now, from here, if you want to find out the value of the resistor, you can directly find it out. That will be V by Ig minus G. That's it. Now we'll see some questions from this topic only. This topic and torque, some of the questions. Just to note down this part, make this circuit diagram, note down these points. Yes, Marita, correct. See, this says that a current carrying coil is subjected to a uniform magnetic field. The coil will orient so its plane becomes inclined at 45 degrees to the magnetic field, inclined at any random angle, arbitrary angle to the magnetic field. Is it parallel, making 0 degree, or is it perpendicular to magnetic field, making 90 degree? So see, coil must be oriented so that magnetic moment becomes parallel to the field. If it becomes parallel to the field, then only the magnetic force on it can be 0, right? Sine theta, we put it as 0. See, this says that current carrying coil is subject to uniform magnetic field. Coil will orient so that its plane become parallel to magnetic field, because magnetic force will then only be 0. Even if you use any of the angles, NAIB you use for torque, if you are using simple BIL sine theta also, unless and until this sine theta, this is equal to 0, theta is 0 degree, for sine this theta, theta is equal to 0 degree. Now see, now magnetic force is 0, right? Magnetic force is 0 on the coil. So that is option C, that parallel to the magnetic field. That's why this is the case possible only when this is parallel to magnetic. Now this question says that the resistance of an ammeter is 13 ohm and its scale is graduated for a current up to 100 amperes. Now after an additional shunt has been connected to this ammeter, it becomes possible to measure currents up to 750 ampere by this meter. So the value of shunt resistance is, Yes, Alia, correct, right answer. Now see, we have to find out the value of this shunt resistance. So see, again, you will be connecting this. This is, let's say, the galvanometer. I'll connect a shunt in parallel with it. Just a second. Yes, so shunt is connected in parallel to this. And let's say current I is flowing through this. This is shunt. All right, so what is the question saying? So obviously across both of it, let's say total current, that the current that passed through here is, let's say, IA. The total current was I. And from here, this will become I minus IA. Right, let me take this as I. Total current is I, out of which IA went to the galvanometer, I minus IA came to the shunt. So just now also I have discussed this thing with you, that if such a case is given to you, in parallel connection, both of your voltages will be same. So IA into R is equal to I minus IA into S. Same thing IG we took. So you can take IG also. IG into G is equal to I minus IG into R. Same thing. It's just that you have to put in the values for shunt will be equal to IA into R by I minus IA. That's it. IA multiplied by R divided by I minus IA. That's it. So CIA, it is given to you as 100 amperes. This is 100. Total current is up to 750. Not is saying. It is saying up to 750. So this is up to 750 amperes. Fine, this is up to 750 amperes. The resistance is saying 13. This is the resistance. So resistance is 13 ohms. Just S is unknown. So this becomes 100 into 13 by 750 minus 100. So this will come out to be 2 ohm. So correct answer as answered by Alia, this is B option. Note down the solution. L is the length of the conductor. Square loop is there, no? So its length. Abhinav and Anna say they have given the correct answer. Marita, some error is there in your answer. See, I'll discuss it. It's like this is the square loop L. So inside it, current will be going. This is L by 2, right? Now a square loop ABCD carrying current I. Okay, the current is I is placed near the coplanar with a long straight conductor XY carrying current I. Okay, I is there in this. Net force on the loop. See, this figure wasn't given to you, no? This is the figure. Without this, how will you solve? L is there, separation between them is L by 2. All right, separation between them, this is going to be L by 2. Now see, L is the length of the loop. This is current XY is placed. Net force it is asked to calculate. So see, force on this, let's say this is A, B, C, D. So net force on this segment, dA. This is going to be mu naught I L divided by 2 pi D. let's say D is, what is the separation? L by 2. Yesterday we had seen this formula, no? Force between two parallel wires. So just consider these two as separate parallel wires. And similarly, force on CD also, if you calculate, this is mu naught IL divided by 2 pi. Now this is going to be L by 2 plus L. The entire separation, this is going to be, this entire will be 3L by 2. So this is 3L by 2. Fine. So now see, if you calculate F net, this is going to be subtraction of both of these. That is, if you take mu naught L common by 2 pi, capital I small I by L common, what will be left? This is 1 by L by 2 from here in the denominator. And this is going to be 2L by 2. So 1 by L by 2 minus 1 by 3L by 2. So net force, this becomes 3L by 2 will go up. L by 2 will be there. 2L by 2, 2 gets cancelled. L. So this is going to be, and here you have 3. So this is mu naught. So 3L minus L, that gives 2. So this 2 that is left, mu naught I small I L divided by 3 pi. What are the options given? I by 3 pi. D option. No, L will be cancelled. No, D option. This L won't be there. No, this L and that L is going to get cancelled. So it's L divided by L. That is D option. So yes, who all answered it correctly? Anna and Abhina. Note this down. We'll see some more questions. See, in an ammeter, 0.2% of main current passes through the galvanometer. If the resistance of galvanometer is G, resistance of ammeter will be C. This is ammeter. So G is the resistance we have connected. .2% means 0.002 of current is going here, and rest 1 minus 0.002, that is 0.9988 current is going here. Now see, 0.002 of current multiplied by the resistance here. This voltage is equal to 0.9988 current multiplied by resistance here. So what is the resistance? 0.002 divided by 0.002I divided by 0.9988I into G, right? This term will go here. So I will get cancelled. How much this will be? This will be 1 by 499 into G. Now see, since net is connected in parallel, so 1 by R, this is going to be 1 by G plus 1 by RS. So 1 by R is equal to 1 by G plus, what is RS that we have calculated? G by 499. So this will become G by 499 will go up. That becomes G by 500. What all options we have? G by 500 is C. C option. Quickly noted.